Hello, everyone. Welcome to our weekly colloquium. And our speaker today, we are happy to have Shira Faigenbaum-Golovin from Duke University. And she will tell us about identifying underlying geometry to denoise and analyze high-dimensional data. Shira, please.
Hello, everyone. Before I start, I just wanted to say that my heart is with you in those very hard times. My family is in Israel now, so I'm very well aware of what's going on. With further ado, I will just go into my talk and talk about underlying geometry. A few words about myself. I completed my bachelor's, master's, and PhD in Tel Aviv University under the supervision of David Levin and Yoel Shkolnitsky. And later I was accepted to Duke University, and now I'm working with Ingrid Debussy, and I'm assistant research professor here. So let's start talking about geometry and data. From my perspective, if before applied mathematics was challenged by phenomena that were happening in physics or most of the applied mathematics, today, we see more and more questions that arise from data, and a lot of data that is available to us from high dimension or low dimension is posing new questions, new mathematical questions that we couldn't even think about before. And I'll try to describe some of the tools that we developed to deal with this data, and what are the open questions, and what do we need to do in the future. So data-driven applications basically allow us to sample data in high dimension, meaning we have some points P, let us call them PJs, we sample them. Common assumptions is frequently that since the data is coming from one domain, we can assume that the data was sampled from a manifold, or there is an underlying structure or geometry to the data. We want to explore the data on its own and say something about global questions that arise in data-driven applications. The first thing that we need to do is to understand how to embed the data in an Euclidean space, whether data is coming from images, when we know that denoising images on their own is challenging, but if we have a collection of images, maybe it will be easier, or probability distributions or surfaces. Basically, each data is possible in our case. And what we are trying to do, the first thing is to perform some denoising operation in alignment. Denoising meaning that we try to denoise the data and find the real underlying geometry while assuming that we are sitting on this manifold. Next, we try to we define some metric, whether it's the classical Euclidean distance or Wasserstein distance between two probabilities, or if we have some the geometry of each point is a bit more complicated, we can define a Taylor distance. And then when we know how to measure those distances, as find similarities and dissimilarities between points, we can try to understand and tailor this geometry from local geometry to the global one. So at times it's hard to understand what is the global geometry, but if we know what is the local geometry looks like, what are the neighborhood of each and every point, and then we are able to find some kind of random walk in each neighborhood. And since those neighborhoods overlap, we can define the general distance between points that are not in the same neighborhood. Once we are able to tailor this geometry, we try to answer some questions that pertain to different applications. In my case, maybe it's coming from archaeology, from anthropology, art history, or others. So there is an underlying research that flow that is going on, and we will try to address the first two items. Item number 2, how to study this geometry and how to do the denoising in this case. So my research broadly can be split out into 3 categories. One is to perform low-dimensional parametric approximation, meaning that we have some data that is sitting in low dimension, because of the simplicity of the data, not that it's really simple, because approximation problems existed already for many years now, but we'll try to define a new function that will approximate those points and will help us to study the geometry. In the high dimensional case, it's much more complicated because we do not know anything about the geometry, especially in from real data. We are trying to understand something locally and generalize it for the global case. And last topic that I deal with is studying the geometry of the data that is driven from different data-driven applications. So I'll briefly discuss now each and every topic now, and you are welcome to stop me in any point and ask questions. So the first thing that I will address today is high dimensional data, where we are sitting in the field of low and high dimensional data. Because of the complexity of the data, we are only able to provide a non-parametric estimation, meaning we are not able to give an equation of the function that will represent those data points in high dimension, but we only can reconstruct the geometry in the broader way. This research direction resulted in 4 papers. The first one published in Journal of Computational and Applied Mathematics, and is basically the basic framework for the reconstruction of data in high dimension and denoising it. And I will be discussing this in more details today. It continued with the work of approximating functions on manifold, which is a very basic question in low dimension approximation theory, but in high dimension it is still open, and we proposed a method how to do that based on our framework that we introduced in the first item. Then we dealt with manifold repairing, meaning that if we have some missing data on the geometry and we try to repair the missing information. And last but not least is compressing the manifold and decompressing it again. The second endeavor that my research is involved in is basically related to low dimensional data, where we have some 1 or 2 dimensional data that we try to find an approximation. Because of the dimensionality of the data, we are able at sometimes to provide a parameterization of the function that approximate this data. So in this endeavor, I have 2 works. One of them is pertaining to answering the question, what are the functions that can be approximated by neural networks? I'll briefly discuss it today, and I will focus on the second item of introducing a new class of functions that will generalize the refinable functions. While the refinable functions are all beloved wavelets, B-splines, subdivision scheme, and fractals. And we show a very easy way that is accompanied with theoretical analysis how we generalize the classical definition. Last but not least is the data-driven applications. I have a series of papers that is related to this field of research, starting from learning the ancient handwriting pertaining to 600 BCE from Judah and Israel, continuing with spectral signatures that was sampled in Israel from soil, as well as comparing different facial expressions based on the assumption that those faces lie on a manifold, and we can treat them as a probability distribution functions and compare them using the Wasserstein distance. The 6th research direction that I'm currently in the last phases of finishing it is comparing biblical texts using some statistical analysis. Last but not least is the shape space research direction that recently I was open to, while we are trying to compare different shapes or different surfaces that were sampled from molar teeth of monkeys and lemurs. If you want to hear more about all of those research directions, let's talk about it after the lecture. And today we'll focus basically on 2 parts. One is the manifold reconstruction and denoising. And the second part is on finding an approximation to those non-symmetric refinable functions. Okay, so let's dive into the details. What are we talking about and where are we standing today? The approximation theory is basically dealing with the following question. We have some data points that were sampled, whether it's in low dimension or in high dimension, and we are trying to find an estimation or a function that will fulfill those constraints. The first thing that we can do is find a linear approximation, which is quite easy. Another thing that we can do is we can demand to create a smooth approximation based on those data points. What happens if we have noise? In that scenario, we are no longer able to provide an interpolation between the data points, but all we can do is find an approximation that will satisfy the conditions. What are the conditions that we are requesting? Basically, we try to minimize the distance of the approximation function from the data point that we have. In the linear case, we can solve it with least squares, but in the more complicated case, there are different methods that we use. The same thing happens in 3 dimensions. If we have a point cloud that was sampled from unknown geometry, we are trying to reconstruct the geometry. And one of the prominent things that we perform today is creating a mesh of those points. And we can perform subdivision schemes or apply them in order to create, in the limit, a smooth surface. So basically, we have some scheme of how to average those local points, and we can perform this over and over until we converge to something that is smooth. In the high dimensional case, it's much more complicated because there's a lot of problems in high dimension. Besides the thing that we do not know what is the geometry that we are trying to reconstruct, we do not know the intrinsic dimension of the data itself and many other things. But we can try to do our best in order to reconstruct the underlying geometry. One prominent assumption that we can make is that the data points were sampled from a manifold. Once we are able to reconstruct the geometry, we can try to address more broader question that is belonging to data-driven applications and talk about the similarity and the dissimilarity between the data points. Why are we so interested in doing that? Well, those points are telling a story. We try to find the approximation or estimate or estimation to the data geometry while having those points. Usually those points has some noise, and we also will need to address this question in our research. So my first topic that I will dive into is high-dimensional non-parametric approximation. What we are given is basically points in high dimension, and we are trying to approximate the geometry of the data. A very common toy example in this case is to play with those Swiss rolls and say that everything works on the Swiss roll. But unfortunately, the geometry in real life is much more complicated and doesn't look like a Swiss roll anymore. We have a lot of challenges. We do not know the dimension of the manifold, and we do not know whether it's a manifold at all. What is the intrinsic dimension? What is the rim, meaning the separation between different topologies on the manifold, and so on and so forth. Applying the classical approximation methods in the high-dimensional case is very challenging. And it all comes from the dimension itself, meaning we do not have enough data points to apply those approximations and get a reasonable approximation order. For example, if we have some data points that were sampled with a spacing of h, where h is 1/L, and we require that there will be L to the power of the dimension d points, already for L greater than 10 and d equals greater than 10 as well, we are demanding a number of points that is practically not feasible to be sampled in many scenarios. So we need to address the problem in different ways. So what do we do? One common practice is to perform dimensionality reduction. And I'm a big fan of dimensionality reduction as well, but you have to be very careful when you're performing that. since you do not know anything about the dimension of the data that you're playing with. And there are a lot of parameters and a lot of assumptions that you make while trying to perform dimensional reduction. For example, what is the intrinsic dimension that you're dealing with? What is the geometry? Sometimes in diffusion maps, we have the diffusion time or diffusion. So how do you tune that in order to capture the geometry of the data at hand? So instead of performing dimensionality reduction, let us stay in the high dimensional case and let us think about our data as sitting on a manifold. Just a short reminder what a manifold is. So basically, we have some data points that were sampled in a lower dimension. Let's call those points tau I. And what we have is some unknown function that is applied to those data points, f, which increase the dimension and embed those data points in high dimensional space. And we have some noise epsilon I that was added to those points. And that's what we observe. Although there is some kind of connection between the points that in high dimension that we observe, we do not know the connection. We do not know the function that created those points, as well as we do not know what is the noise model that we are dealing with. In that case, we will try to reconstruct the geometry of the data without any assumption, which is very challenging. To address that, I've developed the first framework, which I denote MLOP, which is the manifold reconstruction and denoising, that given some sample points that, on a manifold in high dimension with noise, I'm able to reconstruct the manifold in quasi-uniform way, as well as to denoise the data points. This endeavor also continued to other approximation tasks, which I'll also describe briefly later. But let's just dive into the details of this work. So the input parameters are the following. We have some manifold M that is sitting in that was sitting in d-dimensional space. But it was embedded into Rn, as we saw, with some unknown function. And we do not know what is the intrinsic dimension, but we also only know that it's much smaller than the dimension that we observe. We see that there are some points that were sampled from the manifold itself, the P tilde, which consists of points Pj tilde. But unfortunately, we do not observe them. We have some noise that was added to those points in the magnitude of epsilon and j, where the noise is bounded with 0 mean. And that's what we have. We have those points pj, which is basically the original points pj tilde, and some noise that was added to it. And what we are trying to do is reconstruct the geometry of the manifold in noise-free way. We are not looking for an approximation or a function that will reconstruct the manifold itself, because of the high dimensionality of the data. It's very challenging. But only what we are trying to do is find a new subsample of the manifold that will be noise-free. What do I mean by subsample of the manifold? We are looking for a new set of points. Let us denote those Q that will reconstruct the manifold. The problem of manifold reconstruction is very widespread, and it was already addressed more than 20 years ago by the initial researchers that started to think about the problem. However, the problem was hardly addressed in case of noisy scenario, when the data is contaminated with noise and without any assumptions on the intrinsic dimension of the manifold. And that's the strength of the method that we propose. So let us look for those new set of points Q, which are basically QIs. And we demand from those Q points that they will fulfill two things. Two constraints. This will help us to construct the non-convex optimization function. So from the one side, we ask that the QI points will be close to the original PJ points. meaning that we will not go far from the manifold, but we will stay quite close to it. How close? That's what is determined by those weights, Wij, which are basically Gaussians between, and they contain the information of the distance of those Qi points from the Pj's, and we have here H. H is related to the field distance of the points, the representative distance between different points. So we're basically asking to average in each neighborhood of Qi the Pj points in using those weights. What we are looking for is also Qi points that will be spread all over the manifold, and that's what we have in the second term. In case we have 2 points Qi and Qi prime that are getting too close to each other, we have this eta function that has the singularity in 0, and will basically explode and punish those points if they are getting too close to each other. Again, here we have the Gaussian weight here, meaning that in a closed neighborhood of Qi's, we are looking on those separation points between the 2 points. If we think about it in more general form, we are looking for an attraction forces that are pulling the Q points closely to the manifold in local neighborhood, while we have some repulsion forces between the points themselves. They are not, if they are gathering too close, they will just be rejected one from another. And that's quite interesting. So we have now a non-convex optimization function. Let us solve this problem and find the optimal Q points. Also, I should note that because of the construction here, the Qi points will be located in the KL1 median, meaning that they will minimize the distance in each neighborhood from the local PJs, while spreading all over the manifold. And that's also very useful. How many points Qi do we have? As many as we want. If we want to subsample and create a not dense sampling of the manifolds, we can choose that the number of Qis will be smaller than the number of PJs. While if we want to upsample the manifold, we can select number of Qis bigger than the PJs. So what we can do is to perform gradient descent on this optimization function and with some initial initialization of the Qi points. And the question now is whether we converge in this gradient descent iteration at all. It is a very sufficient question because we are talking about non-convex optimization function, and it's not trivial that we will converge. But fortunately enough, we were able to prove that indeed the gradient descent converge almost surely to a local minimizer. We are also able to prove that the approximation order, meaning how well we approximate the original manifold with those Q star points, that is the local minimizer, will be of the order of H square, which H is the field distance of the P points, meaning if we have a good enough sampling of the original manifold, which is quite dense, then we'll have a good reconstruction in terms of O of H squared. Also, we are able to prove that indeed, because of the second term, the result is uniformly distributed on the manifold itself, what we wanted actually to achieve, but now we're able to prove it theoretically also. Also, we're able to bound the number of iterations that the gradient descent will need to be executed in order to converge to the local minimizer, and it depends on the initial sampling of the points from the original points. And we can also say something about the complexity of the algorithm, which is not based on the intrinsic dimension, but only on the dimension where the data is located, and the size of the P set, the number of P points, as well as the number of points in Q, and some other parameters, but which are smaller than the dimension n. Just a few words, how do we prove the convergence of the gradient descent of the non-convex function? So I think the proof is interesting on its own because there are a lot of scenarios when we have non-convex function and it's hard to prove that we indeed converge. And luckily, in 2016, Lee, Schmidowicz, Jordan, and Recht proved the following theorem that under certain constraints on the critical points, on the settle points, we get a convergence. And what are the constraints? That the minimal eigenvalue of the Hessian will be negative. In that case, the convergence is promised. So what we had to do is rewrite our equation in a matrix form, calculate the Hessian. Now we remember that actually we had those W that are the Gaussians, and we can basically write them as some finite support with some small tail. So we will rewrite our Hessian as a sum of two matrices, one that will contain all the finite support of the Gaussians with this small and bounded tail, with an additional matrix that is contain the small and bounded tail. So while all the information is located in the matrix S, we'll have some information that is located from the Gaussians in this delta. We will write and calculate the eigenvalues of this matrix S and see that the smallest eigenvalue indeed is smaller than is negative. We will add some information from the eigenvalues from the delta and combine those two into one using the Burf-Fike theorem. We will be able to conclude that indeed we are able to converge in the given scenarios to a local solution. So after performing all of this detailed theoretical analysis, we were able to run some numerical examples and see how robust we are with respect to noise. The robustness basically is reflected in this graph that even with noise of magnitude of 0.5 from the magnitude of the data, we are still in a reasonable relative error of 0.15. Reasonable based on numerical examination that we did, the approximation still looks very reasonable visually. This also is coming from the fact that remember that I told you that we are performing KL1 medians, and our method also has a breakout point in 0.5, exactly like the usual median. We are able to deal with various data applications. Also, here we see an example of ellipses that were sampled on a manifold with Gaussian noise that was added to it, and this is the before with a lot of noise, and this is the after. We were able to increase the SNR from 50 dB on the left to 36 dB on the right, and we see how clean the data points are. So after observing that we have a very powerful tool, we decided to use it for different tasks. The first one is approximating functions on a manifold, which is a very interesting question in approximation theory. And now what we have is those P points again, with PJs that is run from 1 to K, sitting in this high dimensional space. Also, we have some unknown function that was evaluated in those P points. If we have the values of F of PJs sitting in some RF. And the task is to find a nonparametric noise-free estimation of the manifold as well as denoise the function values F. The solution is quite interesting. So let us define the graph of the function. P hat as the in the following way, where we have the points pj's and the function values in them. It is not very complicated to see that now we have new points that were sampled in a higher dimensional space R n plus s, and actually we have those points were sampled from a manifold in that dimension. Now we are able to, with using this assumption, to apply our MLOP algorithm on the new points P hat and create a new set of points Q hat, which is actually can be splitted to the denoised version of the points from the manifold, as well the denoised version of the function values. And we see how with minimal effort, we are able to address this very complicated question that was studied for decades in high dimension. The other question that I addressed is manifold repairing. In manifold repairing, what we have is data points that were sampled again from the manifold, but some area was not sampled. And there are various reasons why it wasn't sampled before. Maybe there was some occlusion, or we didn't have enough time to sample it, or something else. But the task is to reconstruct the missing information inside those holes. And we also we assume that we know that we need to reconstruct the information in those areas. In order to address these tasks, we basically will need to add additional term to our optimization function that will be responsible for the reconstruction around those holes, and will propagate the information from the boundary of the holes inside. The new term E3 that we introduce here, what is doing is basically for each point on the boundary, and we can recognize the location of the boundary with some heat map that we have of taus. We are doing a weighted average with the local points, and each time we will propagate the points inside. We were able to prove that indeed the new term will perform the propagation, and we're able to bound the error that we'll get inside those holes with missing information. So that was very interesting. I will not discuss the last paper that we just finished in writing. I'll just mention that we also applied the reconstruction on real data stemming from molar teeth of monkeys and lemurs. And this is one example, that we have a surface that was sampled from a teeth, and there is a hole that we identified in this teeth, and we were able to reconstruct the missing information in the hole quite robustly, and use this for the next analysis of those molar teeth. So I think it's a good point if you want to ask something about the MLOP or the other related research topics before I move to the low dimensional parametric approximation. Are there any questions until this point? Okay, so let's move to the other question. We learned what to do in high dimension, where we have those data points and we try to estimate the geometry, but what happens in the low dimensional case? So in the low dimensional case, we have again some data points, and we're trying to find the geometry of the data points. Due to the simplicity of the problem, so to speak, we can actually provide a function definition of those that will satisfy those points. And that's what we'll try to do today. We all know the B-spline, that is basically a smooth function that is created with some equation. And what is the equation telling us? That if we have 4 points where we know what is the value of the B-spline in the point of 2x minus 2, 2x minus 1, 2x, and 2x plus 1, and we have some coefficients, a mask that is given to us, we are able to reconstruct from all those 4 points the entire representation of the spline by simply reconstructing each time additional point in the dyadic rationals. This is also the case if we want to reconstruct the wavelet. We have a closed definition. From several points, we can reconstruct it in very reliable way. In the general case, we can use the following refinable equation and define the general refinable functions. Why is it called refinable? Because we have some values of the function in certain number of points in a support of 0, n, big N, and we are able to use those values just exactly like in the B-spline and calculate the function in the next point of f of x. Also, what we are giving is the Cn, the coefficients, like in the refinable case, in the classical quadratic B-spline are quarter, three quarters, and quarter. Different masks here will result in different functions in the end. So what we see here is basically that once we are having endpoints of the function, we are able to calculate the next level of function values in the next axis. We can use those points again in using the mass that we have to reconstruct the next level of points. And we can perform this operation, what we call the refinable operation, on and on and on, until we will get a smooth function. Okay, that's very interesting. So let us think about those refinable functions again. In the B-spline, we all got a smooth function. But what if I would ask you whether there is a closed definition of all of those functions that I plotted here? And what will be a surprise that I can describe all those functions using only one equation with different refinable masks. And that's the case. The motivation for these refinable equations comes from the fact that the spline is symmetric around 1/2, and basically the points on the positive side can be mirrored and used instead of the points on the negative side. So that's exactly what we are doing. Instead of using the odd locations on from the refinable mask, what we'll do is use the mirror value in the even location. So instead of using the points of 2x minus 1, we will use the points of 2 minus 2x. The same thing will happen for the other odd index of 2x plus 1. We will use instead of it 2 minus 2x. For the even points, we will keep using them as is. So again, instead of using all the odd locations, we will just use the mirror version from the other side. Okay, so let us define this equation in the general case. So instead of using endpoints from the support of this function f of 2x minus n with this refinable mask, let us just split the cases into two. We will use all the even points as we used before with 2x minus 2n with some refinable mask again. But instead of using the odd points, we will just use the mirror version of them with the function values in 2n minus 2x with some different coefficients here. So now we defined a new refinable function that has no longer the support of 0, n. It has a different support size from m to n, and it differs for each and every function, and it has also different masks. What can we deduce from this new equation? Okay, so let us just, I will just say what we know about the previous equation. We saw it in the B-spline case and in the wavelet, that and it was actually proven for the general case that this refinable process converges to Holder continuous function and will also have under certain constraint on the Cn's Hölder continuous derivatives up to some order. So what we'll try to do is also to prove the same results for the new refinable mask. So can we do that? So the answer is yes, but it requested a lot of effort. The first thing that we needed to do is to rewrite this refinable equation in a matrix form, where we define the new vectored value function v of x in two locations. In the odd locations, we will use the reflected value, the f of 2L minus x, while in the even locations, we will use the f of x plus L. So now we have this vector value function. We will define the refinable equation now as v of x multiplied by some matrix of those C and D n coefficients. I will discuss it briefly now. Multiplied by the value of the same vectored value functions in the previous iteration, where we have the sigma, which will basically tell us which points should we use. In our case, we define the sigma as the 10th function, and as opposed to the previous definition that was not continuous in 0.5, in this case, we have a continuity in that point. So now what we do is to define the initial conditions. We will start our refinement operation from the initial points that we are given, the f of n, in the initial points, like in the spline function. And we will define our refinable operation as f of j. We perform the refinement j times using our refinable equation, using that definition of the big V of G. Yeah. Question?
Yes, I'm just not sure that I understand, to see if I understand the setting.
Yeah.
So
the settings are the following. We have a set of points here, and n minus m points.
okay.
And we are trying to reconstruct the entire function using those points, while we are having this mask of Cn's and Dn.
So we know Cn and Dn?
We know them, yeah.
Okay, and then you try to do an iterative process that will converge to
right.
the f,
right.
starting from the data.
Right. Exactly like in the classical B-splines, we know those coefficients. There are some constraints of the coefficients. You can see already one constraint, that some of them sum up to 1. And this is a demand that we'll also ask our coefficient to fulfill. But there are other higher order constraints on those coefficients. So like in the B-spline case, we have 4 points. And from those 4 points, we will reconstruct the entire B-spline. In our case, we have different amount of points and a different refinable mask now, those C and Ds. And we will again perform some kind of iterative process, which will see that it converges to a Hölder continuous function as well, which was a surprise for us because it wasn't trivial. In fact, I will tell you a secret that we tried several different definitions of these refinable functions, and some of them didn't, although they looked very promising, they didn't converge to Hölder continuous functions with Hölder continuous derivatives. And eventually, after 3 or 4 examination of different functions, we were able to find the one that makes sense to us in this aspect. So now we are in those settings. We have those function values. We know the refinable mask, how to perform this iterative process. And now we try to show that we indeed converge to something that is smooth. How do those M0 and M mask look like? They basically contain the coefficients. If in the previous case, on the classical refinable functions, the scenario was quite simple. Those coefficients were actually in the size of the support of the F, and the matrix those metrics would be block diagonal with those size of n. In our case, it's not the case anymore, because we have those coefficients Cn's and Dn's that are coming from both of the sides, from the main diagonal and the other diagonal, and they're filling almost all of the metrics. And that made our life a bit more complicated while trying to prove the convergence. So now we rewrite this equation in the matrix form. We have this V, we multiply it by this matrix B, M, and we decide whether to use the matrix M0 or M1 based on the binary bit of X, meaning that each time we find the binary extension of X and we see whether it has 0 or 1, and based on that, we decide whether to use which of the matrices. And we multiply that, while M are the Cn's here from our original equation, we multiply it by the V, the vector value function, in the previous iterations. Like we had it here before, the F of 2x minus 1, or F of 2x minus 2n, 2n minus 2x. That's how we define those V's. So now that we have this refinable process defined in a matrix form, we were able to prove that under certain constraints on the coefficients that are located in this matrix, the process actually converge uniformly to Hölder continuous function, and we are able to bound the approximation order of this limit of refinement. And next thing, that if we have more constraint on those coefficients, we are able to prove that there exists a solution, and also that exists non-trivial solution, L1 solution to this refinable equation, and that the derivatives of this process are also continuous up to some order, and it depends on the coefficients as well. The proof is a bit tricky because we had to analyze what are the spectral properties of those functions and look on define some new bases where these matrices will be low diagonal, look on their eigenvectors, but I'm not gonna get into more details about it because it was very technical and included a lot of playing around with those convergence of those refinable. But I think that now we have a new equation which is quite interesting. We use twice less points as before because we use only the even points. We have some refinable masks that under certain constraint, we know that it converges to something continuous with continuous derivatives. And now I think a new era opened to us. Like I showed you, we can play with any pre-existing refinable equation and just insert our knowledge to that. So we can define a new set of B-splines that will no longer be symmetric around 0.5 and see what are the approximation orders that they can achieve in various applications. We can define a new wavelets. We can define a new fractals, a new subdivision scheme using this now longer symmetric definition. So we are standing now in front of this huge number of things that we need to do, and that's what basically the future holds. Last but not least, I would like to just address very briefly, because we don't have a lot of time, my last work on approximation theory of neural networks. So neural networks is nothing but a function, a very nonlinear function that we do not, we try to build this function or construct it. Let's think about it, the G function that will approximate some unknown function f. Some people like to draw it in this very complicated way, but it's nothing just of combination and of different nonlinear functions. So in that case, we ask ourselves, how can we, what are the set of functions that can be approximated by those neural networks? I will not go into details of how much work was done in order to understand the theoretical properties of these neural networks, but I'll just say that until now that it was known that smooth functions can be approximated by neural networks and very rough, but there was no understanding of the full picture. And in our paper, we're able to show that if we have a neural network that is very limited and very simple, with one input, one output, and known depth and width, with a ReLU on the nodes, we are able to reconstruct with this network all the class of the functions of the refinable functions, meaning all the fractals in the world, all the wavelets, and so on and so on. And that was very interesting result because it was the first time that such a broad class of functions was added to the ones that can be approximated by neural networks. Later, we were able to prove that our new refinable functions also can be approximated by those neural networks. And that also opened a new vein of research. So we now see that the data in high dimension with noise are triggering a lot of research nowadays. I briefly touched today my two of my main topics that I deal with, but in the future, what I am looking for doing is continue studying those new refinable functions that will introduce us new types of functions, like the B-spline, wavelets, and fractals, and see what the future holds for those functions. I'll continue diving into questions that are asked by and can be dealt with the manifold assumption, which is quite strong with the MLOP framework, whether we can perform some geometry study not only on the manifold itself, but also on the fibers that are sitting on the manifolds. I didn't talk about it today, but it has different aspects that I would like to study, as well as solve PDEs using this framework, but we have some solutions that were given, and we would like to estimate the total solution. Last but not least is a very interesting endeavor that I got involved now is studying the shape space of surfaces that are pertaining to primary molars or to bones, where the assumption is also that those surfaces were sampled from unknown manifold, and we would like to study this manifold and say something about the variation between those shapes. We are not limited to molars or primitive. We can deal with any shape space that we want, whether it's some kind of bacteria or some or the shape of the brains, and see whether it correlates with some interesting facts about the thing that happens there, or whether it's the cryo-EM. So there's a lot of shapes out there. This primary models is only one example for that, and I think that the future holds a lot of interesting things in that endeavor. Last but not least, I hope to continue working about the approximation properties of the neural networks. I hope that by this point you kind of were convinced that I know how to approximate the geometry of the data. So why not to use the geometrical properties and study the connection between that and the type of neural networks and complexity that we'll need to build. So this is some of my collaborations that pertain to my current research, whether it's collaborations from computational polyography that I was involved in, or to those Maya figurines that I described briefly, the evolutionary anthropology, or the biblical studies. And of course, I'm really enjoying working with David Levin, Ingrid Debussy, and Ron DeVour on the approximation stuff. And I would like to thank you for the attention. If you have any questions, I would be happy to answer them.
Let us thank Shira for your magnificent talk.
Thank you.
Now, questions, comments, remarks.
I have a short question. Something I don't think I quite understood. So the wavelength is not necessarily symmetric, right?
Right.
So what does this reflection do? How is it advantageous if it's not symmetric to begin with? Because at least as far as I understood, if you start with a spline, then you have this symmetry built in. But if it's not symmetric to begin with?
That's a good question. Basically, I think that's what we'll need to understand in the future. We will define those new non-symmetric wavelets again, but we'll need to understand how are they better than the previous one. We didn't study it yet. We are just in the phase of finishing the theoretical analysis in the general case, and I think that we'll need to still do that.
But you cannot get these new functions from some kind of, an initial scaling function or some function, a scaling function. So this is a new set of functions that you get. You cannot get it by changing something in the original wavelet construct.
Yeah, we can't get it by the previous one. That's why it's so interesting, because to approximate those very unique and non-symmetric functions, we had to probably work very hard, and now we have a close definition how to generate them. And this is something that was never existed before. So
okay, thank you.
Other questions?
I have a question. First of all, thank you, Shira, for your interesting lecture. You mentioned several times Wasserstein distance. And my question is if it's the same distance we use in transportation optimization problems.
Right. It is the same.
It's the same.
It's the same distance. Yeah.
So you use tools of transportation problems, right?
Yeah. So what is happening is that in a lot of image processing applications, we can look on the images that we have as distributions and compare them using exactly those optimal transport tools. In our case, the images are noisy, so we also had to perform some analysis on the robustness of the optimal transport in those scenarios. So that although we were applying that to a very specific problem, but we also were able to identify some mathematical problems that we can tackle later. So that's basically what I have to add about it.
Yes, and one more question. You mean the Wasserstein distance is using the integrals, right? But in transportation problems, we have also discrete version. I mean, Kantorovich-Rubinstein distance. So do you use also this kind of metrics? I mean, discrete case of the transportation problems.
Yeah, in the discrete case, since we have those images which are basically they are discrete cases, so we are using the discrete case of the Wasserstein distance. We are not using the general form, but together with Caroline Mussmuller, she developed, maybe you're familiar with her works, she is in UNC, Wasserstein distance that is very efficient, but for the discrete case, and which can deal efficiently with such problems of optimal transport. So that's what we are using.
Okay, thank you.
More questions or comments?
As far as I understand, basically you need to compare two distributions, probability distributions, but there are other ways like Hellinger distance and a few other notions. You could even cut Wasserstein distance, if I remember correctly. Why specifically Wasserstein distance you are using here?
Well, that's a good question. We tried some other distances, and that was provided us with a better result on some ground truth data set that we had, and we kept just using that. We didn't examine all the distances from probability comparison in the world, but just examined several ones, and it showed to be like better than the others. So that's the only reason.
It could be quite difficult to use Wasserstein distance. For example, version where you cut Wasserstein distance requires less data, maybe could be better, could be useful, I don't know.
Maybe if you can just send me the reference to that paper that you are addressing, then I will be happy to read about it more.
Thank you.
You mentioned when talking about high dimensional data, you mentioned reconstructing TIFF. The same. In what sense is the data about TIFF high dimensional? Because I could imagine position in space and maybe some composition. So in what sense is it high dimensional data?
Yeah, so the TIFF data is actually surfaces, so it's not really high dimensional data. So in that case, it was just simple surface reconstruction, but for the task of reconstructing the TIFF, it will later be used in the other scenarios of the application. When in the project of studying the shape space of the TIFF, we are in a high dimensional case because each TIFF is actually the point on our manifold, and we have now a collection of TIFF. So we are sitting on a manifold in high dimension and looking on the geometry between those TIFF. But the reconstruction of the TIFF, it was just applying the method, the MLOP, on something that will be useful for later.
Other questions? If not, let us thank the speaker again.
Thank you. Thank you for your attention.
Thank you very much. Next week, Hanukkah, there is no colloquium, so בשורות טובות and happy Hanukkah.